Okay, so now I think we'll skip some of it and then go to uh, one important section of this class. This is we're at page 112, 112. Okay, so now we're going to the multiple signal case. So before multiple case, we would a, a quick review for the binary case. So usually when we are doing a detection problem, we are actually making a decision on which one is the truth, right? We are always asking a question, which one is the truth? That's the fundamental question, and we have been asking this question from day one of this class, right? So, in binary case, in binary case, we will have here H0 and H1. That is the basic one. For example, that I have been asking a simple question: is it raining outside? Right? Is it raining? And let me just assume that it is either raining or not raining. Of course, there are sometimes small rains and people are unable to distinguish, but let's just um, just make it simple, saying that is it raining? If it's not raining, then it's H0. If it's raining, then it's H1. So it's a simple question. Or, for example, a BPSK case, binary phase shift. In such case, you are detecting a digital communication example that is either you're transmitting a 0 or transmitting a 1, right? Um, so in different scenarios, those signal model may represent different things, but uh, in here we will just mathematically model it, and then you need to interpret it in the context of your research. It really depends. Okay, so uh, in such cases, we have H0 that has S0. Previously, we always assume this part to be 0, but to be more general, we will not assume it to be 0 anymore. We will just assume there is a signal that's called signal 0, and it's disturbed by a noise W. And now H1 has a signal S1, and S0, S1 are non-deterministic signals. Okay, and then of course W is the sigma square. So we do this likelihood ratio, and it has been done previously. So it's just a quick review. And then uh, as discussed previously, this is a maximal likelihood rule. So if we write it out in a more general sense, we are assuming Hi instead of H0 and H1. Uh, just notice that when we are assuming the subscript to be I, meaning that I has many options. It could be H0, it could be H1, or it could be H0, H1, H2, H3, H4, so on and so forth. You can go on and you get many hypotheses in your case, right? For example, let's say if I throw a dice, how many faces do you have for dice? You have 6 faces. As a result, you're going to have H1, H2, H3, then up all the way up to H6, right? 6 hypotheses. So in this example, P of x conditional hi will be equal to this because of what? Because it's multivariate Gaussian. It's multivariate Gaussian. So you have this multivariate Gaussian distribution, and then you have this is also Gaussian and summation x minus the mean. The mean is of course its signal. If you just recall what happens here, you take the expectation. This Sn is S0n is going to be the mean of this x. Okay, so now we have probability density function looks like this, and then we decide h1 for which d square di square is minimum. Is minimum. Uh, so this is the probability density function, and when x is observed, this becomes a likelihood function. So we will decide h1, no, excuse me, hi for which this is the minimum. How come? Think about it. Think about it. For different i's, this is the same. This is the same. The only difference is this part. This is corresponding to this, right? As a result, when this term is minimum, it has minus term in front of it and it's in the exponent. As a result, when this is minimum, it actually corresponds to the maximum of the whole thing. So it becomes the maximum likelihood. Okay, so is that understandable to you? If not, take it easy and slow down a little bit and think about it clearly because this is a very fundamental concept. So I'm going to say it again. This, if this is the smallest, which is the minimum, this whole thing is maximum, which corresponds to maximum likelihood. As a result, we will decide hi for which this is the minimum because this minimum d squared is going to give you the maximum likelihood. Okay, so but here we can also call it minimum distance receiver. Minimum distance receiver. And if we consider the data and signal samples as vectors in Rn, then of course this is a vector version representation for this thing. Okay, and then this known representation. This is Cauchy square equal to Cauchy is a square Euclidean norm in Rn. Of course, it's just a vector norm representation. And then we will choose the hypothesis whose signal vector is closest to x. Then this is intuitive, right? We will choose the hypothesis with the signal vector closest to x. So here we sort of summarize a little bit. We try to find the hi that has the minimum d squared, which is consistent with maximum likelihood, which is also consistent with the hypothesis whose signal vector is closest to x. So everything is intuitively reasonable now. Okay, so now we sort of give a more general sense of this. Let's say now you have in the vector space you have S here, then you have S0 here. You have only two hypotheses. Now you're getting a signal here. You try to calculate the distance of this and calculate distance. You find out that X is actually closest to S0. As a result, you will decide H0. That's reasonable. Uh, then the other thing is if we look at the vector space and then we see that S1 is located in here, S0 is located here. And now we are trying to find the region for smallest distance. What will we find? We are actually finding a line, sort of maybe a hypersurface. If it's in hyperdimensional space, high dimensional space, then it will be a hypersurface. It's a high dimensional surface, and it will sort of cut in the middle of the two signals. And then in this region, whenever your observation appears in this region, you always say it's x0. Whenever it appears in this region, you always say x1. And that's consistent with what we see here, the minimum distance receiver. Under Gaussian assumptions, this minimum distance receiver happens to be the maximum likelihood receiver. Okay, so uh, minimal distance receiver, of course, then we can check this example 4.6 carefully, and then we will find that, of course, I'm not going to repeat all the details here. You can take a look, and we'll calculate D, and then we will just do a little simplifications, then we get this Ti. We'll decide Hi, for which this Ti of x, which is equal to this one, is maximum. Is maximum. Okay. So uh, if we just take a look, the receiver will look like this. The minimum probability of error receiver. How come? Take a look at this again. You are correlating your observation with your signal and then minus 1 over 2 epsilon I. Okay, this is the signal's energy. As a little reminder. And then if we are implementing this thing, then it will look like this. You have your observation comes in, and then it goes to correlation with this S, and it goes to correlation with this, and you do the summation, then you sort of minus this epsilon 0 minus epsilon 1. That's kind of the bias. How come there is a bias? Because we derive it here. We derive it here. Okay, then uh, eventually test statistic condition on H0, condition H1 goes in, and when you choose the maximum, okay, you choose the maximum. If T1 is larger than T0, then you choose H1. Otherwise, you choose H0. Okay, so that's kind of the 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 test statistic and also its block diagram. And the performance is like this. You have your PE equal to P of H1 conditional H0. However, it has a prior probability P of H0. If that is the case, then you have to multiply by its prior. In digital communications, usually we will assume 1/2 for each hypothesis equal prior, but in many cases it may not be. So we multiply by its prior and conditional, we are making a mistake on that ground truth H0, and the same applies for H1. Okay, so we do derivations. So for example, the probability, prior probability is equal, and that's 1/2. And for this larger than that, this larger than that. And then eventually we we go to the step where we have to calculate the expectation of t condition on h0. The same, right? This is the same thing. Then we do the derivation. Then we come up with this this kind of this kind of equation. That's the expectation for t condition on h0. Then of course, eventually it goes to a minus 1 over 2 s1 minus s0. Similarly, similarly, aspect of this, you can do the derivation if you get this minus e t condition on h0. Also the variance, then we do the same thing and do simplification, and then we get this. And then similarly, we do it for h1, we get something like this. So as a result, here is what's really interesting. We have a probability density function of t condition on h0 and t condition on h1. And then their mean have been calculated as this minus 1/2 s1 minus s0, or minus, and then you can do the mean and then distribution, and also the mean and then distribution. That has been all calculated. Then what's the error? If we just look at this PDF, the error is going to be because you're making decisions on this. Therefore, this area is the error for h1, and you are making a mistake on h0. And this area is the error in which the truth is h0, you are making a mistake for h1. So this is one type of error, the other type of the error. So as a result, we can calculate this. This is as we did before by Q function or something like that, right? So PE is kind of PR of this, and then conditional H0, T is something like this. This has been derived previously, so that PE is Q function of this thing, this thing. Finally, then PE will be Q function of this thing. Okay. So, as we discussed earlier, if this increases, P decreases. Is this reasonable? The answer is yes, because when the signal distance increases, of course, we will expect the error to be decreased. So this is intuitively reasonable. Intuitively reasonable. Okay, so this is the PE for the binary case. Then there is a case for phase shift keying, and things like that. Okay, then of course, then other examples include frequency shift keying, FSK, and then here comes the other thing, that is the M-ary. That's the more general case. Just to so that you can follow, we are at page 119. And M-ary case, we come from binary to M-ary. So now we have M signals, M hypotheses. We have S0, S1 originally. Now we are going from S0 to Sm minus 1. Then again, we're not going to prove it here, but the optimal receiver is again the minimum distance receiver. So we are going to choose HK if this is the maximum. This is the maximum. Then what happens is we have signal correlated with your target signal. For example, 0, then that will be 0. Index subscript 1 will correspond to signal 1. Subscript 2 will correspond to signal 2. Then minus its signal energy as some kind of adjustment. And this is actually the maximum likelihood, but except that we are not deriving it here. But actually, it's not that hard. You can just write the probability density function out, and then you take the common terms out, and then eventually you get this as the test statistic. So we now come up with a set of T0, T1, all the way to Tm minus 1. Then the optimal receiver is in figure 4.13. So we will take a look. Just review one more time. We are trying to using a block diagram to implement this. Well, now next step is going to implement this. So we will have a M-area detector. When your signal comes in, this is very important because in many cases you're going to encounter such scenario. Other than just binary, you're going to have M-area, and that signal observation actually comes in, and then you correlate with S0, you correlate with S1, correlate with this, and then you do summation, and then you do adjustment for the signal energy, and then eventually you come up with this, and all the way up down to here. Then you choose the maximum. For example, if you have got 1, you have 0 to 5, and H3 T3 is the maximum, then you will choose H3. That's the maximum likelihood here. So that gives you a decision. So that's kind of the maximum likelihood detector. So in this chapter, we have been going from binary case to M-area case. And the most important thing is that you understand this is the maximum likelihood test statistic. And also you understand how we implement it in block diagram. And that is in this figure. So I think it's very important that you get a sense of what it is. And there are some illustrations. So for example, 4-QAM. If we are talking about digital communications, 4-QAM is the standard 4-area detection problem. So you have error probability that goes down here, right, with this SNR, things like that. So I think that will be the end of this chapter, and then also the end of this week. And we are going to move on uh, next uh, from chapter 5, and that will be next week. And thank you for listening.